Hello, my name is Roy Simpson. I'm a professor of mathematics at Kissimmee River College in Sacramento, California. This is the final lecture on functions for intermediate algebra. We have already gone through the definition of a function, domain and range, a bunch of different ways we can represent functions, function notation evaluation, graphing functions, doing point plotting, that type of thing, and then all of a sudden doing base graphs and transformations of those base graphs. We're now going to venture into some more advanced features of function notation. We'll go ahead and start this section with a talk about evaluations of functions here. If we're going to evaluate a function at a variable or an algebraic expression, the work that we go through doing this actually is basically the same amount of work that we do when we evaluate at a number. For example, this part A here, where we're looking at h of 3k, well, I happen to know that h of r is equal to 5r squared minus 2r. When I'm asking what h of 3k is, it's essentially saying wherever I see an r in the original function, replace that with the value 3k. So what I'll do is I'll go ahead and rewrite this as 5 times something being squared minus 2 times something. And in that place that used to be r, I'll replace that with 3k. And when we do that, we'll get 5 times, well, 3k being squared is just the same thing as 9k squared minus 6k. Well, that's going to be 45k squared minus 6k. We can play this game all day long. If we're looking at h of k plus 3, again, the function looks like 5 times something being squared minus 2 times, well, something else. Instead of being r's, we're replacing everything that said r with k plus 3. And now we use a little bit of our algebra skills here. K plus 3 quantity squared is just going to be k squared plus 6k plus 9. And then I'll distribute this negative 2 to get a negative 2k minus 6. I'll distribute this 5 to get 5k squared plus 30k plus 45. And again, minus 2k minus 6. And finally, combine like terms here. So I'll get a final answer, maybe I'll write this in blue so you see it's a final answer, of 5k squared. Let's see, we have a positive 30k minus 2k is a positive 28k. And finally, 45 minus 6 is a positive 39. The next example, h of k plus 3, don't get too confused by this example. We're just looking for what is h of k. So the first thing I'm going to do is write 5 times something squared minus 2 times something else. That will be h of k once I insert the letter k for all where the unknowns were, where the r's were before. In fact, I'll write that in blue. So wherever I have an r before, I'm going to replace with k. And then this statement right here is the original, is h of k. To that, we're going to add 3. So that's h of k, and then to that we'll add 3. So this should equal 5k squared. Oh, and again, I'll actually write this, maybe I'll write this in a nice color as well. So actually black is good. 5k squared minus 2k plus 3. So each time you evaluate a function here, or you're asked to evaluate maybe a combination of a function and a constant or something like that, every single time you see I am rewriting the function with blanks. Again, this one, h of negative k, is equal to, well, 5 times something squared minus 2 times something. Remember, h has this form. And instead of writing an r in here, I'm going to write a negative k. And this actually will equal, let's see, 5, well, negative k times negative k is k squared. So this will equal 5k squared And then negative 2 times the negative k is a positive 2k. Finally, well, actually not finally, we have f up above there. We're being asked to evaluate h of 4k squared. It's actually not going to be much different from the other ones. We have 5 times something squared minus 2 times something. Those somethings were r's before, but now they are 4k squareds. And all we're going to do is clean that up. Basically, it's 5 times 16k to the fourth minus 8 times k squared. And our final answer here will be 80k to the fourth minus 8k squared. This final example above here, h of k, quantity being squared, is essentially saying this. I have something being squared. That something is the function h, which was 5 times something squared minus 2 times something. And remember, inside that something, I was going to use the letter k. So wherever I see something to plug in for my variable here, I'll plug in k. Now clean this up. This is going to equal quantity 5k squared minus 2k and quantity being squared. And that'll be 5k squared minus 2k times 5k squared minus 2k. Oops, I almost forgot the k there. And now I'll distribute through. And when I do that, I should get, let's see, a 25k to the fourth. You can check my work here. Minus 20. Let's see, I'll get k cubed. And then finally, plus 4k squared. You can check my work, multiply that out yourself. It should actually come out to this. So that's one set of examples of how to do more advanced work with functions. Another set of examples is something like this, where you're actually asked to compute the value of a function plus the value of the function at some other value. So the function is negative 5 over x, and we're asked to find f of 1 plus f of 8. So let's see, f of 1 is going to be negative 5 over 1, wherever I see an x, I'm going to plug in 1, plus a negative 5 over, and again, wherever I see an x, I'll replace it, in this case, with 8. We'll have to find a common denominator here, which is going to be 8 itself, so I'll multiply top and bottom of this first fraction by 8. That's a negative 40 over 8, plus another negative 5 over 8, so our final answer will be a negative 45 over 8. Always reduce fractions in the end, but this one does not reduce at all. The next example, we have f of 1 plus 8. Notice the difference between these two examples. The first example was asking us to evaluate the function at 1 and then add to that the evaluation of the function at 8. Here, this is asking us to actually evaluate the function at 1 plus 8. That'll be negative 5 over, and wherever I see an x, I'll replace it with 1 plus 8. Now I know some people are saying, well, why couldn't I have just written that as 9? You could have, but I'm just trying to show you that these two fractions are going to be different. This is going to turn out being a negative 5/9, which does not reduce. So notice that f of 1 plus f of 8 is not equal to f of 1 plus 8. At least in this case. Some functions it's true, but most functions it's not. Let's continue this forward. We're looking at f of a plus f of b. So this is going to be kind of a continuation of example a here. F of a is going to be negative 5 over, and wherever I see an x, I'll replace it with a. And to that, I'm going to add f of b, which is a negative 5 over, and wherever I see an x, I'll replace it with a b. The common denominator between these two fractions is AB. So I'll multiply the first fraction by b over b, which is just 1. And the second fraction by a over a, which again, just 1. So I'm not really changing the size of the fraction, just the look of the fraction. And so I get this, negative 5b minus 5a all over the common denominator of ab. Do not make the dreaded mistake of canceling a's and canceling b's. That's a stupid move. Yes, I did say stupid move, because what you're doing is canceling across addition, and nowhere did anybody ever tell you you can cancel across addition. In fact, just to show you, what you would normally do to cancel something is you maybe, if you wanted to, factor that negative 5 out of both those terms. You get negative 5b plus a over ab. If there was a 5 downstairs, you could cancel these 5's. But because there is no 5 as a factor in the denominator, there are no common factors between the numerator and the denominator. You cannot cancel the a or the b. All right, f of a plus b, well, that means take the function f, and wherever I see an x, I'll replace it with a plus b. Actually, that's as good as it gets with this one. This is just going to be negative 5 over a plus b. There's no other way to simplify that down, really. You can't break this apart, so let me put this in red. This is not equal to negative 5 over a plus a negative 5 over b. It's not equal to that. Remember, addition, I said it in the past, maybe with some other lectures, but addition and subtraction do not work the way you want them to work. Whatever you want to be true is likely not. You would love this to break apart, so therefore it's not true. Now let's take an example here that is really generally very difficult for algebra students. I have a graph here of a function. Let's call this function f. So this is going to be the function f here. And I'm going to ask a few questions. First question I'm going to ask is, I want to know the distance between the point S, the vertical distance between the point S and the point R. So maybe I'll write this down here. Part A, find the vertical distance, not the actual distance between those two, but in other words, this distance right here. So find the distance between S and R vertically. And because there are no real numbers in this situation, all you can use are the concepts of a function. Now, the height at this point here, what you need to do is, what might actually help is actually to label that point. The point itself has an input and an output. The input is this value down here. I'll highlight it. This is the entire x value. The x value is a plus delta x. And I don't know if you recall, possibly not from a past lecture, that the delta implies, well, that's a horrible delta. Delta is another way of saying change in. So this is saying we have some point A plus some change in x. So our input is A plus some change in x. A might have been 1 and that delta x might be 5. So that'd be 1 plus 5. Okay. The height at of this point, or in other words the function value at this point, is going to be f evaluated at this point, a plus delta x. So you have the input and the output. And this is the very technical notation with functions. Now, the easier point to look at actually is this one over here. This point has an input of a and an output of f of a. That's actually the easier question to answer. Now, I want to know what's the vertical distance between these 2 points. Well, if this height right here is f of a plus delta x, that's the y value because that's the point, that's the y value associated with the point S, and this point right here has a y value of f of a, then the distance between these two y values, or these two outputs, or these two function values, whatever you want to call it, is going to be, well, the difference between those two. It's going to be, well, maybe I'll write this in black, f of a plus delta x minus f of a. That's how you can use function notation intelligently. Now, to ask a question that's more related to a future course, and anybody who's taken calculus knows this question, find the slope of the line connecting point R and point S. Now remember, slope is just difference or change in y over change in x. Change in the y value over change in the x value. Now, this notation specifically has a very neat, very cool understanding here. So let me draw a line between these two first. And now let's talk about the slope of that line. Well, we happen to know 2 points on that line. One point is a, comma, f of a, right? The input, the x value is a. The output, the y value is f evaluated at a. The other point is a plus delta x. And the output for that is f of a plus delta x. So the difference in the y values, and I usually take the second point as my first y value, so f of a plus delta x over its corresponding x value, which is, or input value, which is a plus delta x, minus, and then the second y value over the first x value. In other words, so we have this, I call it the second y value, but really I'm just going to say this group of points, the output over its input, so f of a plus delta x over its input, a plus delta x, minus, and then the second point, f of a over a. And now let's simplify this, because actually that denominator can be cleaned up a little bit. So we find out that this is equal to, draw a line here, f of a plus delta x minus f of a all over, well, a minus a, that cancels, so all over delta x. Now, this is a hugely important concept in calculus. It is actually the beginnings of the derivative. Very, very close to the idea of the derivative. So a very neat idea here. And to know how to use this notation is very important, actually. So please spend some time kind of reviewing this video lecture and really trying to get this. Now, there are a lot of other topics when you're dealing with functions. Specifically, there are things called compositions and inverse functions, things like that. But actually, those two topics, inverses and composition of functions, actually go hand in hand. And that's not going to be for this lecture. I like to save that talk right before you get into like exponentials and logarithms, because really that's when knowing how to work with an inverse is very important. So there are a few other topics and functions that I'm going to kind of delay for now. But this last little topic is a very interesting topic. It's actually how a lot of functions work in real life, piecewise defined functions. And a piecewise defined function is essentially a function that's been broken into parts depending on the value of your input. They take on a form like this, where you have a function g of t, which is equal to, and then you have this brace, and this brace splits it apart into cases. If t is less than negative 2, then your function is equal to this, 3t plus 9. However, if t is greater than or possibly equal to negative 2, then your function g of t is equal to negative 3 minus 1/2 t. So let's take some values here just to see what this looks like. Let's look at g of, let's say, negative 5. So the first thing you do when you're asked to evaluate a piecewise defined function is you look at these conditions. You say, okay, is negative 5 less than negative 2? If it is, which it is in this case, then I'm going to go ahead and use 3t plus 9. In other words, it's going to be 3 times something plus 9. That's the winner. The other one, negative 5, is definitely not greater than or equal to a negative 2. So that one I don't bother using. And wherever I would have had a t, I'll replace it with a negative 5. And so g of negative 5 is going to be a negative 15 plus 9, which is equal to a negative 6. All right. Now let's try another one here. Let's try g of negative 2. So in this case, let me go ahead and erase my little check mark there. In this case, again, I'm going to check my conditions. Is negative 2, our t value, is that less than negative 2? Definitely not. Is it greater than or possibly equal to a negative 2? Absolutely. So g of negative 2 is going to equal a negative 3 minus 1/2 times something, and that something used to be a t, it's now going to be a negative 2. And when you do the mathematics here, this is equal to a negative 3 plus 1, or in other words, it's equal to a negative 2. As a final kind of evaluation example, let's try g of, I already started writing it, g of 5. And again, I'm going to go ahead and erase those right there. G of 5, again, I look at my conditions. Is 5 less than negative 2? Definitely not. Is 5 greater than or equal to a negative 2? Absolutely. So this will equal a negative 3 times a negative, or minus, sorry, 1/2 times something, and that something is going to be 5. So this is going to be negative 3 minus 5/2. That's a negative 6/2 minus another 5 of those halves. So altogether, it's a negative 11/2. So there's an example of how to evaluate a piecewise defined function. Actually, it's not so bad. You just kind of look through your conditions and make sure that your function or that your value that you're evaluating the function at meets whichever condition you're trying to plug in for. The more interesting part actually is when you want to graph these. So let me go ahead and show you how to graph this. So I have my t-axis and I have my y-axis, which is actually my g of t. Okay. And I notice that when t is less than negative 2, so let me mark off negative 1, negative 2. When t is less than negative 2, it looks like 3t plus 9. And you should probably notice that 3t plus 9 is a linear function, so it's just going to be a line. And you can either, I know some instructors that just say, well, graph the function and erase the part that's greater than t, where t is greater than negative 2. I usually don't do that. I usually just plot a couple points that are to the left of t equals negative 2. But you could do whatever you want here. I'm just going to try, well, I already have g of negative 5, and then I'll try g of negative 2. G of negative 2 actually is a great one to use as well. Not really g of negative 2, but this y equals 3t plus 9, I'm going to evaluate that at negative 2. So at t equals a negative 2, this function is going to turn into a negative 6 plus 9, or in other words, 3. So I know that it's up here at a height of 1, 2, 3. And I'm incorrectly labeling that right now, but for now, this is I'm okay with that. And then I'm going to try maybe g of negative 5 here. So we did negative 2. And as I look at g of negative 5, I actually already know it's going to be way too negative. So let me just try g of negative 3. So I'm going to, again, at t equals a negative 3 this time, you get that the function, at least for this graph right here, it's going to be 3 times a negative 3 plus 9, which is nice and 0. So I have something like this, that point, and then it goes through negative 2 comma 3. Negative 2 comma 3. And I'll connect those points up with a line, but before I do, I have to make mention here that at t equals negative 2, it can't be on this line, okay? Because the fact is that I've already said that when t is equal to negative 2, it's the function depends on the other line. So what you do in that case, you put an open circle there, meaning that this line exists all the way up to t equals -2, but not actually at t equals a -2. Erase these little dots here so I can clean this up. Okay. Now for the second half, so that was the first half of the piecewise defined function. For the second half of it, I'm going to plug in, again, t at -2 exactly, and we've already done that luckily, so we know at t of -2 exactly, that second part is going to be at a height of -2, so it's going to be down here at a height of -2. And then I'll plug in another value, and remember, this time I'm looking at y equals a -3 minus 1/2 t. So I'm going to probably plug in a value like t equals 0 here. So at t equals 0, we get that y is equal to a -3. So let me go ahead and plot that. And now I can connect these points up. And now because it's going to look like that line for all t greater than -2, I can keep graphing because for all t greater than -2, and all these t values here are greater than -2, so it's just going to be this line from that point forward. That is a graph of a piecewise defined function. You have a first half and a second half. Sometimes piecewise defined functions can be very busy. You can have a lot of pieces, so it doesn't necessarily have to be just one half and a second half. It could be broken into 5 parts, 6 parts, 7 parts, 8 parts. The most important part, though, well, it's all kind of important, but what's really important is I want you to be able to recognize when to make a dot solid and when to make an open hole. Open hole when you cannot actually be equal to that point, and solid dot if you can actually be equal to that point. So let's try one last example here. We have a function d of x, piecewise defined, split into two pieces. We have that it looks like the absolute value of x if x is less than -1, and it looks like x cubed if x is greater than or possibly equal to -1. So let's go ahead and plot -1 first. So what I mean by plot is just mark off where -1 is, and I will break this into halves. So in other words, each little step in the x direction is a half, and each little step in the y direction on this grid is a half. Okay, so now the first thing I usually do, again, is that I go ahead and say, well, if x is -1, so let me let y equal the absolute value of x. I'll concentrate on this first function first. And I'll say, well, if x were a -1 and we could plug it in there, then what would this function be? Well, y would be 1. So I'm going to go ahead and go up here, and I'm going to put an open hole. In fact, maybe I'll use a different color here. I'll put an open hole at a height of 1. Because remember, I can't actually be at x equals -1 for this first graph. But I know that it would be basically like that. And now I can try a value of x that's lower than -1. For example, let x equal -2. If you do that, y will equal 2. So go ahead and go over here to -2, and y will be a +2. I'll fill that in with a solid. And now we can connect these 2 points. And you carefully graph this out. Remember, the absolute value curve was supposed to look like a V, but we're cutting off most of it. Now, let's go ahead and go to the second function. So that was the first function. The second function, or second part of this piecewise defined function, is that it looks like x cubed if x is greater than or equal to a -1. Now, to be honest with you, we know what x cubed and what absolute value of x looks like. X cubed looks like this. And so, really, I know that on the right-hand side here, it's going to look something like, I mean, not exactly like, but something like that. Okay. And it'll scoot around here and it'll come down here. Now, just make sure that you've that you're going through 0, 0 because, well, the cubic function does. Cubic function goes through 1, 1, and it goes through 2 comma 8, but I know that I didn't really draw this like that, so oh well. And it also goes through negative 1 comma negative 1, which this one does, and it's solid at that point. So this really is a graph of d of x, which is this piecewise defined function. Sometimes you don't have to plot points if you know the base graph, which we happen to know at this point. And so if you know the base graph, you can just quickly graph that. And like I said, some instructors teach that they just say, oh, you know what, graph the absolute value of x, and then, so here's the absolute value of x, and then erase off the stuff where x is bigger than negative 1. So you'd go, okay, well, let me erase off the stuff that's bigger than x equals negative 1. There we go. And that'll give you the proper part for that piece. Do the same thing with x cubed. I want you to be good at this stuff without having to graph things and erase things, though. So give it a whirl without over graphing.